has 13 bus system, out of which there are 5 generators and the remaining 9 plus 5, sorry 8. How much? 13 minus 5? 8 load buses. So here there are 8 load buses and 5 generator buses. Let us consider this system. Let us consider this is the slack generator. So P1 is the slack generator. P1. So P first is the slack generator. Rest are the buses. So I have sorted all the variables. The recurrent variables are unknown parameters. For each bus, recurrent variables are unknown parameters, and P1 is not known, Q1 is not known, Q2 is not known, Q3, and similarly V6, V7, V13 are not known. Delta 2 to delta 13 are unknown parameters. What are known? For all buses, P's are specified except the slack generator, and similarly Q's at all load buses are specified. Now the problem is, for P2, the unknown parameter is delta 2. For P3, the unknown parameter is delta 3. Similarly for P13, delta 3. And here Q6, V6 is unknown. So, if you want to solve a problem, the number of variables should equals the number of equations. So, the number of equations and number of variables should be equal. If the problem, if the problem has this problem has 2 variables, 2 equations, then only the problem can be solved. For this problem, there is unique solution. If the number of variables are more than the number of equations, then there will be infinite number of solutions. For example, you consider this. The number of equations is 1, but the variables are 2. If you substitute, if you put x1 is 0, you will be getting another x2. If you make it 1, you will be getting another value. So there will be infinite number of solutions. So if you want unique solution, the number of equations must equal the number of variables in the problem. So for this load flow problem, the number of equations P2 to P13 similarly is delta to delta 13 are variables. Similarly for Q6 to Q13, P6 to P13 are the variables. It equals. The number of variables equals the number of equations. Clear? So these unknown, the recurrent parameters are to be determined at the end of load flow analysis. That is the problem. Right? We have already seen equations. So in this case, P2 to P13 are the variables. P2 to P13 are the functions. So P2 we have to explicitly write the equation. P3 we have to explicitly write the equation. Similarly up to P13. So P2 to P13 we have set of equations in terms of, instead of x here we have vi, vj, cos delta a, delta j. That's all. So the problem is, instead of x here we have v's and deltas. That's all. And similar to this constant, this 10 and 15, here we have constant of specified parameters 1.5 minus 0.27 something like that. These are all the right hand side variables. The difference, this equation minus this should be equal to 0. So the problem here for this problem is to find the values of v's and deltas that will make the mismatch 0. This minus this should be 0. This minus that, this equation. So the problem for this part is to find v's and deltas, the values of v's and deltas that will satisfy all the 12 equations. Clear? It is very similar to these two, these two simultaneous equations. Of x1, there b and deltas. Clear? Similarly, there is another set of equation, that is q6 to q13, 8 equations. The values of q's are specified. The 8 equations and 8 unknown parameters. There is another set. So totally earlier 12 plus 8, 20 equations now we have. 20 equations we have. We have 20 nonlinear equations, we have to solve it, that's all. The variables are v's and deltas. If you can solve, if you can apply some technique to find v's and deltas, then that problem is load flow solution, load flow problem. Right. The formulated problem can be solved using the traditional mathematical techniques. So those methods were already developed long ago. for mathematicians. So one of the important is Gauss seidel, Newton-Raphson, and later depending upon the characteristics of the system, power system, we have developed decoupled Newton-Raphson and fast decoupled power flow. These two methods, but these two methods are traditional mathematical techniques. So Gauss seidel, do you want derivation? No, right? Let us avoid that. Okay. So in Gauss seidel, this is the final equation. So Gauss seidel, what we do is those equations we calculate first bus voltage, then second bus voltage, third bus voltage, fourth bus voltage. So the available quantities can be substituted in this equation, and we will be calculating one by one. What we do? So we initially assume a set of voltage. If you do not have any values, all voltage magnitudes are assumed to be 1, all angles are 0. Simply substitute all the values, solve this equation, you will be getting first V1 new. Already we have initial values, from that we will be calculating V1 new. Similarly V2 new, V3 new, V4, V5, say if it is a 12 bus system, V12. Once 12 is completed, then we have to check whether the previously calculated value and the previous values are same. If both are same, we obtain solution. If there is difference, once again the recent values are considered to be old values. Once again repeat the whole process. So again you will be getting a set of another values. Repeat this till the values between two subsequent iterations are same. For example, mathematical, let us consider a simple example. Initial value is say 2, then 2.1, 2.2, 2.3. For example, this y equal to x square, this problem. The final solution is 3, 2.5, 2.67, 2.9, 2.99, 3.01, then 3.001, then 3.001, something like that. Then it will become 0.001, then 3.00001. So if the difference between two subsequent values are very small, then we will terminate. We can't exactly make it 0 because computer even 0.1001 maybe is not considered as 0. So the difference between two subsequent values are less than small tolerance of 0.001, then we will say we have obtained the solution. So in that way the problem can be solved. So it takes, the problems are, we do not use these days this Gauss seidel method because it takes more number of iterations. But the main prime advantage is it is very simple. It is easy to understand. Within 15 minutes we can write a program to solve this equation. It requires less computer memory. It doesn't require, except OMS, we do not store anything. So it's slow due to poor rate of convergence. Why it is? Because the coupling between one equation and the other equation is less. Because one equation, if you see the system Chennai, the Chennai may be coupled to Kalpakam, the nearby places, only 3 or 4 places. If you think of the whole India, it's no way connected to Delhi, it's no way connected to Bangalore. It's connected to neighbor places, nearby 3 or 4 places. So each equation is coupled to only 3 voltages. 3 voltages and 3 powers. Okay, Bangalore is coupled to the nearby 4 places. Delhi is coupled to the nearby 4 places. So the coupling between Chennai equation and Delhi equation, there is no mutual coupling between these two equations. So there is very less coupling between one equation and another equation. That's why it slowly converges. It slowly moves toward the final solution. So because of that, the number of iterations increases. For example, if you consider only small region, the number of iterations may be 10. If you consider Tamil Nadu, the number of iterations may be 20. If you think of India, the number of iterations may be 100. So number of iterations exponentially increases with system size. So we cannot say we will get solution at the end of 5th iteration or 6th iteration. And here choice of slack bus also affects convergence. If you choose first bus as slack bus generator, it may take 10 iterations. If you choose second, it may take 15 iterations. So it has so much of influence. So these are all the problems associated with the Gauss seidel, and that's why we are not using this Gauss seidel for powerful analysis these things. The next powerful technique, most powerful technique is the Newton-Raphson method. most powerful method. I have said, earlier I have formulated two sets of equations. One is P set, another one is Q set. Those two equations can be simplified, mathematically represented by these two things. P of delta comma V minus P specified equal to 0. Q of delta comma V minus Q specified equal to 0. Simple, because the first represent the first 12 equations, second represent 8 Q equations. First of. So we have used it mathematically. It can be represented like this. Then this is basically a nonlinear problem. We have to linearize the problem in terms of correction variables. So P is of delta plus del delta, comma V naught plus delta V minus P specified equal to 0. This we represent the problem in terms of correction variables. Similar to that one here, this is mismatch delta F. Similar to that, we are just simplifying the equation by applying Taylor series. The problem can be expanded like this. Again, Taylor series is a mathematical process. We linearize the nonlinear equation by this process. P of delta comma V naught plus dou P by dou delta into del delta. This way we can linearize the equation. Here we are ignoring the higher order terms. And this can be converted into matrix form. So dou P by dou delta, dou P by dou V. So dou Q by dou delta, dou Q by dou V. So the equations we have seen earlier can be partially differentiated with respect to variables, and we can form Jacobian matrix. So Jacobian is very popular in almost all fields, all engineering fields. Not only engineering, even the statistics problems they use Jacobian. Okay, that is derivative matrix. And this is mismatch vector P specified minus P calculated value. Similar to this. 9 minus 2 square. Similar to this, 9 may be specified and this may be the calculated quantity 2 square. Similar to that, we can calculate mismatch, and this can be arranged in this form: dou P by dou delta. This is correction vector. This is the mismatch vector. And again, this is called Jacobian matrix. This is correction vector, mismatch vector. And in general, once you form the Jacobian matrix, and if you study the values or if you observe the equations, what happens in the upper half, and if you compare the upper half and lower half, only one variable is missing. Yes, only one variable is missing. Because of that, the lower half of element will be different from the upper half of the element. So only one variable is missing. If you add that variable, both will be equal. So 2, 3 will be equal to 3, 2. If you can make that, then we can calculate only one half, and other half will be simply mirror image of the upper half. So the calculation part can be drastically reduced. For that reason, the missing component can be added perfectly. The Jacobian term dou P by dou delta into V. So this part V is missing. With respect to V, we can add V's and V's here. And here, if you add anything, that can be eliminated. So multiply the equation by V divided by V. Nothing. Okay. So intentionally we are adding this V. So this V and V gets cancelled, but because of this addition, the whole matrix is symmetrical, and upper half will be the mirror image of lower half. So we can simply calculate the upper half, the lower half can be simply copied. So that drastically reduces the competition time. This is the mismatch vector, and this equation is repeatedly solved. We have to assume a starting value of P and delta. If not available, all voltages are assumed to be 1 per unit and angles are assumed to be 0. Then if you do that, the first step would be form Y bus matrix. Initially is all bus voltages. Calculate delta P, that is mismatch between real power and the calculated values, and calculate Q at all buses. What happens at the end during the process? What happens? The Q at the genetic stations may violate because it has lower and upper limit. It violates. If it violates, we have to bring back to within the limits. It should lie within the limits. So for that purpose, we have to check for Q limit violations. If it violates, then that bus may be treated as PQ bus, or we have to do some measure to reduce the voltage. If you reduce the voltage, then Q will decrease. If the voltage Q exceeds, voltage should be slightly decreased. If Q falls below the lower limit, voltage should be increased. So that kind of measure we have to do. So for that purpose, if it is compute delta Q, check for convergence. Check for convergence means we have to check whether delta P and delta Q are small, very very small. For example, for this problem, 9 minus 2 square is 5. We have to check whether this is very small. If not, proceed. If the difference is say 4, again proceed. If the difference is 4, 3, proceed. 1, proceed. 0.01, proceed. 0.001, proceed. 0.401, stop. That is the solution. So in the similar fashion, we have to check whether delta P and delta Q are smaller, less than a small tolerance value. Check for convergence. That is the check for convergence. Then form Jacobian matrix. Jacobian matrix means what? The problem. This previous one. This is the Jacobian matrix. If it is not convergent, form this Jacobian matrix. Then solve that equation. How do you solve? Jacobian inverse into the right hand side vector will give the correction values. How do you solve? Once this is formed, find the inverse. This inverse with delta P and delta Q will give the correction vector. Solve this equation. You will be getting del delta and delta V, update delta and V. That means update means what? Previous value, the correction value, both will be added. You will be getting the new value. Solution. Then go to step 3. Step 3. Once again calculate delta P using the updated delta and V. Repeat this process till it converges. Converges means what? Delta P and delta Q are smaller, sufficiently smaller. So that is the process. But the Newton-Raphson, it takes 2 to 3 iterations irrespective of system size. Whether it is Tamil Nadu system or Indian system or whole world system, it takes only 2 or 3 iterations in general. Okay, that is it, because it has quantity convergence feature. It has quantity convergence feature. What that means? At the beginning, the iteration, the error may be 0.01. The difference between this calculated and specified will be 0.01. The very next step, it becomes 0.40. All of a sudden, the drastic change. From this directly this, again it becomes point something like this. This feature is known as quantity convergence feature. Rapidly decreases. Rapidly decreases. That's why it takes less number of iterations and insensitive to selection of slackness. Whether it is first best or second best, it does not matter. It gives the solution with the same number of iterations, and number of iterations independent of system size, as I mentioned earlier. Whether it is Tamil Nadu system or Indian system or a whole world system, it takes the same 2 to 3 iterations and computational. But the problem is it is really computationally inefficient. Inefficient in the sense it requires inverse. We are familiar with the matrix inverse of 3 by 3. If I give you a problem of size 3 by 3, you can do hand calculations, you can find inverse. If I give you 4 by 4 matrix, you may take at least 2 hours. 2 hours to find the inverse for 4 by 4. But the system, if you think 100 plus system, then as variables are approximately 200, we have to find 200 by 200 matrix inverse. Even for computer, it is a time-consuming process. There are alternate approaches that is called AV factors and other things. Still, all these procedures require large computation time. That is the prime drawback of this Newton-Raphson. It's a powerful technique. That's why this method cannot be used in online power systems. That is the great drawback of this problem. So to improve the speed of that Newton-Raphson method, the feature that is decoupling feature, decoupling between P's and Q equations. In general, if you make small change, then that will cause a large change at this point. Change may be 0.01. The angle, the change will be 0.01, whereas the change will be here 0.001. If you make any change for real power, that will have significant effect on bus angles, and it will have very negligible effect on delta V. Similarly, if you make delta Q small change 0.2, for this case it will have insignificant effect. Here it will have significant. If you make 0.2 change for delta P, the large change will take place in delta V, and here it will have very negligible effect on this. That means there is strong coupling between these two and strong coupling between these two. there is weak coupling between, the coupling between these two is weak, and similarly the coupling between these two is weak. The coupling between, that's called decoupling. Decoupling. So based on this, in the Jacobian matrix, this is dou p by dou delta. It is large. Dou q by dou v, it's large because of this. But whereas dou p by dou v, it is very very small and it can be neglected. Similarly, dou q by dou delta, it is very small. It can be neglected because the values are very very smaller. So neglecting these two, we can neglect the off diagonal blocks. So the equations can be splitted into two separate equations because we decouple. The first equation represents dou p by dou delta, delta v is equal to delta p. So second set of equations. So this represents the first equation. This represents second equation. The problem can be split into two small problems instead of larger problem. Say for example, 1000 bus problem. Say the size of the whole matrix is 1000. Instead of 1000, 500 by 500, two small 500 by 500 matrix can be inverted. So in that way, if you do that these two equations can be alternatively solved. Because of that, the number of iterations slightly increases, but still the execution time, the overall computation time is lower than the previous example, previous Newton-Raphson method. It takes less computation time. But problem is, it takes more number of iterations because we are changing the direction of solution. We are changing because the Jacobian quantity Newton-Raphson gives like this. First iteration 3. So it directly moves to that point. Whereas if you do approximations, if you make any approximation to the Jacobian, it gives wrong direction. That means what? Instead of this direction, it gives this direction. Because of that, this is wrong, but it has to move that direction. Again it gives wrong. Then it moves here, then moves here, like this. Finally it reaches. So it takes more, instead of 3, it takes 7 or 8 iterations. 7 or 8 iterations to reach the final point because we made approximations in the Jacobian matrix. We made approximations and we removed 2 portions. That's why it takes more number of iterations, but still it takes lesser computation time. Okay, this is called decoupled Newton-Raphson method. Right. Again, most of the transistor systems, if you study, the resistance values are very very less compared to reactance value. The resistance can be neglected, and today's power systems are well compensated systems. Well compensated means all loads are locally compensated by reactive powers. So the need for reactive power flow is totally eliminated. So with that assumption, the problem can be further simplified based on these approximations. Cos delta I minus delta j is equal to 1 because if the system is well compensated, the angle difference is very very small, less than 10 or 20 degrees. Cos of smaller angle will be equal to cos of smaller angle, cos 0 is equal to 1. With that approximation can be, so the terms containing cos of delta I minus delta can be replaced by 1. So wherever we have in the Jacobian matrix, wherever we have cos term, that can be replaced by 1. Similarly, the resistance is very very smaller than the reactance. All resistance can be eliminated. So in the Y-bus matrix, we can have conductance and susceptance. Conductance can be totally eliminated, and all voltages are assumed to be 1 per unit. So the difference between any two buses are very less. So all voltages are assumed to be 1 per unit. With these assumptions, the Jacobian matrix can be further simplified into this form, that is B prime and B double prime. B prime is nothing but the negative of imaginary part of Y-bus matrix. So already we have Y-bus matrix. From that we can pick the elements and we can, without any calculations, we can form this B prime and B double prime matrices. Once these two are formed, it can be inverted and permanently stored in the computer. During the solution process, we need not form B prime and B double prime. We need not find inverse, so it is readily available. So the problem is we have to find only the mismatch into already available inverse matrix. Inverse matrix mismatch will give the correction. Similarly, inverse matrix into this correction will give the mismatch will give the correction. Repeatedly solved. So this is very fast. That's why it's called fast decoupled power flow method. I don't want to explain the derivation part because it's available in the textbook. Derivation I have brought, but still, if you ask any doubt, then I will get into that. Otherwise, let us not discuss those equations in detail. So these two are the basic equations. These two equations are alternatively solved. This is very fast, and the present day energy systems uses this as an online power flow method. Online power flow method because it is very fastest, but it takes more number of iterations. Newton Raphson takes 3, decoupled takes 7, this takes 50. But still, it takes this like this. It takes like this. It takes more number of iterations because it involves large approximations, but it does not require any formation of Jacobian. It does not require any inverse of Jacobian. So the overall execution time is 1/10 of the Newton Raphson method. But still, it gives the solution. It gives the good solution. So the problem is it cannot be applied to all systems because there are certain assumptions. If any of the assumption go invalid, then the algorithm will not give the solution. It does not converge. It does not converge. It oscillates. It will never settle to a final point. So that is the problem. For example, for a system, if voltage difference is not closer to 1 per unit, it will not give solution. If the resistance are large, it will not give solution. For example, resistance should be 0.001. If we put 1 as the resistance, it will not give solution. Okay, 1 per unit, sorry. So that is the drawback of this. So it exploits decoupling. Jacobi matrices are constant, do not require to be recomputed. Computationally efficient, requires more number of iterations. Diverges if any of the assumptions becomes invalid. Cannot be applied for distributed systems. Distributed system, it has wide ranging resistance and reactance values, and it is suitable for online applications. This is the fast decoupled power flow analysis. So there is another important power flow analysis because present days most of the researchers are working on distributed systems, microgrids, distributed systems, reconfiguration of systems, optimal DG placement in the microgrids, distribution systems. We have to run load flow. We have to, as a researcher, we have to perform this load flow analysis, and again, the same Newton Raphson method or any other method cannot be directly used for all distributed systems because the behavior of distributed systems are totally different from transmission systems because distribution systems are radial in nature, whereas transmission systems are highly interconnected. So for example, Chennai is connected to number of points, whereas distributed system, there is one substation, it may grow to this point, next place. Then there may be extension, something like this. It grows in this fashion like a tree. It grows. These are all the extensions. So say for example, Anna University, if some developer proposes another Nagara nearby, then there will be a radial feeder, right? So it grows in this way, grows like a tree. So in general, distribution systems are radial in nature. This radial nature itself causes problems, induces problems in the solution process. And not only that, the voltages cannot be assumed to be 1 per unit because the substation voltage is 1. Here may be 0.99, here may be 0.98, 0.97 because of voltage drop. So for tail end, the voltage may be 0.88. So 0.88 cannot be considered as 1 per unit. So the voltages are not 1 per unit in all places. Not only that, this is lower operating voltage system, lower operating voltage system, whereas transistors are higher voltage systems. And here, this system has wide range of resistance and reactance values. The resistance cannot be neglected. Some places they may use cables, some other places overhead lines. Right? Some other engineer will buy something and lay. So it's not perfectly designed system. So the system will have wide range of resistance and reactance values, lower operating voltages, radial nature. Because of this, it's considered to be
conventional load flow methods are not.
It cannot be directly used. It gives solution. Newton Raphson gives in general solution, but it's not be yes. I have forgotten the terminology. So it's not considered to be a stable system. Okay, I have forgotten the name because I have not prepared anything for this lecture, so I have forgotten. So, but anyhow, So the traditional methods are not suitable. So the methods are classified into I have pointed out wide range of resistance reactance, radial structure, wire optical. And we have to frequently run load flow even in distribution substations. So here number of methods have been developed by researchers in the recent decades. One is node based method, another one is branch based method. Node based method is very similar to neutron based method. So it has mismatch and other things. And another one is branch based method wherein the Kirchhoff's current law and voltage laws are applied. Laws are applied. Based on that, two versions. I have brought two versions. One is branch based method, another one is branch power based, another one is branch current based. Let us focus on the second one, branch current based distribution, because I see you are all tired. So let us wind up. Branch current based, because you can easily understand. Branch current based distribution. So this is the branch current based distribution. Let us consider this simple example. I have brought a 7-node example. It is a simple system, right? So the current, load current, J represents load current. Load current at any point can be calculated using this. The power, the specified power divided by the voltage will give the power, will give the current. So the current at any point can be calculated using this equation. In general, for loads, load can be modeled as either constant power, constant impedance, constant admittance, or something like that. If the load is modeled in impedance form, VI divided by ZI will give the current. If it is in admittance form, YI into PI into the form will give the current. If it is current load, straight away current can be substituted. So any form, depending upon the availability of loads, you can substitute the values and you will get the current J1, J2, J3. So for a sound bus system, J1 to J7 can be calculated. These are all represent load currents. At the beginning, voltages are not known. That is the problem. The problem is to find voltages. Voltage is not available. So you can assume the initial the substation voltage. It's 1 plus J0. That is assumed as all bus voltages. You can evaluate the J1. Once J1 is calculated, then J1, J2, J7 are known. Once these currents are load currents are known, then the current through this branch 7, this feeder 7 is nothing but the current at the load point 7. The current J7 is the feeder current. The feeder current 6 is the current at node 6. So 6th node is nothing but J6. 7th node is nothing but J7. What about this 5th node? 5th node is equal to, 5th feeder is equal to this J5, J6, J7. So I5 is equal to J5, J6, J7. Similarly, J4 is equal to this feeder 4 is equal to J4, J5, J6, J7. J4, J5, J6, J7. In this way, we can write the expression for all branch currents. Once these branch currents are calculated, formed, then that can be transformed into matrix form. Here right hand side, J1, J2, J3, I1, I2, I3. So first row contains all ones. First row must contain all ones. Otherwise there is something. There is disconnection of line. So the first row must be 1, and here this is the matrix. This matrix is called branched mode matrix C. IV is equal to C into J. Okay? J is set of load currents, C is this matrix, IV is the branch current. So this C matrix can be formed from the network. J1 can be calculated from the first equation. These are all the branch currents. Okay. Similarly, branch voltage drop. Branch voltage drop is, what is the branch voltage drop? The current into impedance will give the voltage drop. So the V1 is equal to Z1 into I1, V2 is equal to Z2 into I2. So V into Z diagonal Z matrix, Z1, Z2 are the line impedances. So you will be getting, so this can be VB is equal to Z into IP. Similarly, the voltage drop in line 1 is equal to Yes. Yes, yes. No, previous V1, V2 are the branch voltage drops. Right? So this E01 is the voltage drop between source node and first node. So let us come to the previous diagram. This diagram. The voltage, this voltage drop is known, this voltage drop is known, this voltage drop is known. The voltage drop between source node and this voltage is nothing but the voltage drop in this branch. The voltage drop between 0 and 2 is this voltage drop plus this voltage drop. The voltage drop between 0 and 3 is this voltage drop plus this voltage drop plus this voltage drop. That means the net voltage drops can be calculated by this equation. This equation. So this gives the voltage, the effective voltage drop between 0 and 1, 0 and 2, 0 and 3, substitute into fourth node, 0 and 5, 0 and 6, 0 and 7. So the voltage drops can be calculated. So once voltage drops are calculated, then bus voltages can be substation voltage minus drops. Substation voltage minus drops, all bus voltages can be calculated. So once this is calculated, we have to compare these voltages with previously assumed values. If both are same, we obtain the solution. If not, we have to once again calculate or come to this point. Once again calculate using the new voltage. We have to once again calculate load current, branch current, then branch voltage drop, then effective voltage drop, then bus node voltages. It's called nodes instead of bus. Buses are used in transmission systems. Nodes are used in distribution systems. That gets the point. So this process may be repeated till it converges. Convergence means the values between two subsequent iterations are same. So read system data, form C matrix, set VA is equal to V naught, calculate load currents, calculate branch currents, calculate branch voltages, compute node voltages, check for convergence. If not converge, go to step 4, calculate load currents, repeat this process till it converges. So this is known as the distribution power flow matrices. Distribution power flow. It reliably converges for all systems. Reliably converges for, I got the point. Ill-conditioned systems. Distribution systems are considered to be ill-conditioned systems that may not give solution for all power flow problems. So for ill-conditioned systems, this method effectively works because it does not require any Jacobian matrix. It involves only Kirchhoff's current and voltage laws. So in that aspect, it gives solution. It is simple, computationally efficient, reliably converges, and it is robust. Robust in the sense, the variation of R by X ratio will not influence the final solution. It always gives the solution in that aspect. In that aspect, this method, this distribution power flow method is very effective especially for distributed systems. It cannot be extended for drawback is, it cannot be extended for other analysis. For example, Newton-Raphson method can be extended for optimal power flow, right? But in that way, it cannot be extended for other methodologies. But this is very essential for optimal placement of capacitor, optimal placement of DGs, or any reconfiguration, etc. So this power flow is very important. Right? If you have any doubt, we shall discuss. Otherwise,
You said a load model can be either the load model.
yes, any load model can be used here. In this case.
Say for example, if it is a constant current load and constant impedance load are almost combination. Because it is not
Listen. Constant impedance load is different from constant current load because constant current load. Constant current load means whatever may be the terminal voltage, it draws the same amount of current, say if it is for 10 ampere, whether it is 200 or 210 or 220, it draws the same current. It automatically adjusts its parameter in such a way that it draws 10 ampere current. That is constant current model. Constant impedance means the impedance may be same. If it is 200, the current will be one thing. If it is 210, it will be different. Okay, that is the constant impedance model. Constant power means whatever at rated voltage, it draws that much of power.
change according to, because still they observe the same current. So the nodal voltage is not held at some particular voltage, but still it observes the same current.
Yes, whatever may be the, yes, that is constant current. That is constant current. Whatever may be the voltage drop, whatever we think, once it is excited, because it's a nonlinear load, maybe quadratic based load, it adjusts its firing angle in such a way that it draws the same amount of current. Okay, that type of load is called nonlinear, constant current.
What for the exterior equipment?